Hey everyone, welcome. Today we're going to talk about a really cool piece of tech that can seriously speed up your software. It's a tool for unlocking all that parallel processing power that's just sitting inside your computer, waiting to be used. We're talking about OpenMP. So let me just start with a pretty wild promise. What if I told you that you could take your existing code, add just one single line of text, and poof, make it run massively faster? I know, it sounds a little bit like magic, right? But this is the core idea behind OpenMP, and we're about to see exactly how it pulls it off. So you might be asking, why do we even need something like this? Well, it's pretty simple. Pretty much every computer these days has multiple processor cores. You can think of them as individual brains. But here's the catch. Most programs, by default, are written to run serially. That means they run in one straight line, using only one of those brains at a time. All that other power, it's just sitting there, doing absolutely nothing. And that's exactly where OpenMP comes in. The key word you want to focus on here is incrementally. See, unlike a lot of other complex parallel programming tools, OpenMP was built from the ground up to let you take the code you've already written and just gradually teach it how to use all those other cores. It's designed to be approachable. All right, so let's learn our first spell. We're going to look at the simple, almost magical way OpenMP gets things going, and it all boils down to a special little instruction you give to your compiler. That instruction is called a pragma. Just think of it like a sticky note you leave for the compiler. With OpenMP, that note always starts with #pragma OMP. Now, if your compiler understands OpenMP, it follows the instruction. But, and this is the really clever part, if the compiler has no idea what OpenMP is, it just ignores the line completely. That means your parallel code can still run as a totally normal serial program on any machine, no changes needed. Let's look at the most classic program of all time, Hello World. We just add one line, #pragma OMP parallel, and that's it, we've cast the spell. That single directive tells the system, hey, that next block of code, I want you to run it with a whole team of threads. Seriously, it's that simple. And you can see the result right here. On the left, you've got your standard program. It prints one line, nice and predictable. But on the right, our parallel version prints 4 lines, one from each thread. But check out the order. It's all jumbled up. That's because all 4 threads were basically racing to the finish line, and there's just no guarantee who's going to get there first. This right here is the visual proof that our code is actually running in parallel. So what's really going on behind the scenes? Well, it's a concept called the fork-join model. Your program kicks off with a single master thread. The moment it hits that #AMP_parallel directive, it forks, kind of like a road, creating a whole new team of threads. This entire team then executes the code inside that parallel block. Once they're all done, they hit this invisible wall, wait for everyone to catch up, and then they join back together. The extra threads disappear, and the original master thread just keeps on going. Fork, execute, and join. That's the whole model. Okay, but you know the saying, with great power comes great responsibility. The second you have multiple threads working at the same time, you're gonna run into your first big monster on this programming quest, the race condition. So what in the world is a race condition? Well, imagine you've got a shared variable, let's call it total. You tell 4 different threads to each add a number to it. You'd expect the final total to be, the sum of all 4 numbers, right? But because all the threads are basically tripping over each other to update that one variable, the final result can be just wrong. Let me show you exactly how something as simple as 1 plus 2 can end up equaling 2. Okay, walk with me here. Let's say the total starts at 0. Thread 0 reads the total. It sees 0. But before it can do anything, thread 1 also reads the total. It also sees 0. Now thread 0 does its math and writes its result 1 back to the total. Great, the total is now 1. But then thread 1, who still thinks the total was 0, writes its result 2 and completely overwrites the work that thread 0 just did. The final answer is 2, not 3. That's a classic race condition. So how do we tame this beast? Well, the most direct way is to create something called a critical section with #pragma OMP critical. This basically tells all the threads, hey, one at a time in here. It forces them to line up and take turns. It works, sure, but it also creates a massive performance bottleneck. Kind of defeats the purpose of being parallel. A much, much better way is to use the reduction clause. You just tell OpenMP, hey, I'm doing a sum on this variable. Then OpenMP handles all the complicated synchronization stuff for you, super efficiently behind the scenes. It's smart enough to give each thread its own private copy to work on and then combines all the results at the very end. Okay, now that we know how to handle our shared data, let's look at what is probably OpenMP's most powerful feature for beginners, automatically parallelizing loops. But, as you're about to see, this power comes with a pretty big hidden danger. This is the part where OpenMP just feels like pure magic. You can take a totally standard for loop, the workhorse of so much of our code, and just add one line right above it. Hash pragma OMP parallel for. That is it. OpenMP will automatically take all the iterations of that loop and split the work up among your threads. If you've got 1,000 iterations in 4 threads, each thread's going to get about 250 of them. It almost feels too easy. And sometimes it is too easy. Take a look at this. We're trying to calculate the Fibonacci sequence, where each number is the sum of the 2 that came before it. On the left, you see the correct sequence. On the right, that's what happens when you just slap a parallel 4 on it. The first few numbers look okay, but then you get zeros, a complete disaster. So what happened? Well, one thread might be trying to calculate the 8th number, but to do that, it needs the 6th and 7th numbers. And if the threads responsible for those haven't finished yet, our thread just grabs whatever garbage values are sitting in memory, which in this case happen to be zeros. This problem has a name. It's called a loop-carried dependence. It's any time one trip through a loop depends on the result from a previous trip. You see, OpenMP is powerful, but it's not a mind reader. It can't magically solve these logical dependencies for you. It's on you, the programmer, to recognize when this is happening and know that parallel 4 is just the wrong tool for that particular job. All right, so you've written your code, the logic is perfect, you've dodged all the race conditions and the loop-carried dependencies, but it's still running slow. It's time to meet the final boss of our quest, a performance killer that is completely invisible in your code. This has to be one of the most frustrating things in performance tuning. You feel like you've done everything right on the software side. The logic is totally sound. So why isn't it faster? Well, the answer isn't in your code. It's in the hardware that's running it. So let's take a real quick detour into computer hardware. Your CPU has a tiny amount of super fast memory right on the chip called a cache. Getting data from this cache is lightning fast compared to going all the way out to your computer's main memory, the RAM. To be efficient, when the CPU needs some data, it doesn't just grab one little piece, it grabs a whole chunk of nearby memory called a cache line. And this is the key part. That one cache line might be holding several of your variables all squished together. And this brings us to this weird phenomenon called false sharing. I've got a simple analogy for you. Imagine 2 people living in separate apartments, but they share one really noisy water pipe. When one person turns on their sink, it makes a huge racket in the other person's apartment, even though they aren't using the water at all. They're not really sharing the water, but they are sharing that pipe, and it's causing all kinds of interference. So here's how that plays out with our CPU. Let's say thread A is working on one variable and thread B is working on a totally separate variable. But by pure chance, they both happen to land in the same cache line box. When thread A writes a new value, the hardware, in its infinite wisdom to keep everything consistent, invalidates the entire box for thread B. So a moment later, when thread B needs to access its own variable, its copy is gone. It's forced to make a slow, super expensive trip all the way back to main memory, even though its specific variable was never even touched by thread A. And that, my friends, is false sharing. It's this nasty performance problem where your threads aren't really sharing data in your code, but they are falsely sharing a cache line in the hardware. The very system that's designed to prevent errors ends up forcing your threads to constantly go back to slow memory, and it can absolutely kill your performance. So, let's recap our little programming quest here. We've seen that OpenMP can give you some incredible power, a lot of times with just a single line of code. We learned how to beat that race condition monster with the super elegant reduction clause. We know to watch out for the parallel 4 trap, those pesky loop carry dependencies. And finally, we unmasked the invisible final boss, false sharing, which is all about how your data is laid out in memory. And that kind of leaves us with one final thought. We started this whole journey looking at the obvious parallelism we could unlock, but we ended up discovering a performance problem that's completely invisible in the source code itself. It makes you wonder, doesn't it? What other invisible bottlenecks are hiding in the code you're writing every single day?